Welcome back, and now we want to talk about how do gases behave. So in previous lessons we have talked about how solids behave when you apply a force to them, and we've also talked about how liquids behave when you apply a pressure to them. So now we want to talk about how do gases behave. And gases are more complicated to talk about because their volume can change when you apply a pressure to it. And normally solids and liquids, they don't do that, so we call them incompressible. So now we're going to be talking about gases. And so here is our formula for a gas, and you can see that it's pressure P of the gas multiplied by its volume V. And notice that I put hooks on my volume when I do that, so not to confuse that with like velocity. And then it's going to be equal to N, which is the number of air molecules, and then multiplied by a constant, K, called the Boltzmann constant, and then multiplied by temperature, T. So it's a kind of a complicated formula, and what I'd like to do is derive it for you using conceptual concepts. So imagine that you have a solid, like a block, and that you want to move that block, and you're going to move it a distance r. Well, in order to do that, you're going to need to apply a force to it, and this is going to take energy in order to move the block. And so we found out in a previous lesson that that was called work. So work W is equal to a force multiplied by a distance. When you apply a force to a block, it makes the block move distance r. And so this is going to be the amount of energy that it's going to take in order to move that solid block. But what about if it was a fluid? So we don't talk about forces when we're talking about fluids, things that can flow. And so what I'm going to do here is multiply this by A over A. So that where A is going to be the area of this end of the block. So now what we've got is a force divided by an area, and then a distance multiplied by an area. But this thing here, force divided by area, is going to be pressure, and then this is going to be volume. So therefore, if it's a fluid, if it's something that can flow, then the amount of energy that you need to put into it in order to get that fluid to flow is going to be the pressure that you apply, and then multiplied by the volume of the fluid. And so we learned about this in a previous lesson when we talked about liquids. And a liquid is a fluid, it can flow. So now what we want to do is apply this to a gas. So this was work, which was when you transfer energy into a system in an organized manner. See, every atom of this block is moving the same distance r, so that's organized. But what about if it was a gas in which it's composed of all of these gas molecules that are moving in all sorts of different directions? Well, that's not organized. That's going to be disorganized. And so what was the type or what was the manner in which we could move energy into a system in a disorganized manner? What was that called? That was heat. Okay, so what we're going to do is, instead of doing work on it, we're going to apply heat to it. So it's still going to be PV on one side, so this is what it's doing. The energy is causing the pressure and the volume to change, but the energy that we're going to put into it is going to be heat. And then what was the definition of heat? Okay, so it was an energy that was proportional to the temperature. So that if you raise the temperature of a gas, then you increase the amount of energy that goes into it. Okay, so what we're going to do is set that equal to this side over here, and we're going to say, and instead of equals, let's put a proportion symbol and say that it's proportional to the temperature. So now we got PV is proportional to the temperature. This is the energy that's going in, and then this is what the energy is doing. And then let's put in the constant of proportionality so that this is an equal sign. So then this is going to be equal to KT. Okay, so this is the constant of proportionality, which is called the Boltzmann constant, and that's this number up here. And then finally, we want to know what is the total energy that is going into the gas. So this would be the energy of one of these molecules, but what would be the total energy? Well, we would need to multiply by the total number of air molecules that's inside the box. So then finally we end up with N, K, and then T. So that is going to be the ideal gas law. It says that the pressure of a gas is going to depend on the volume of the gas, the number of air molecules inside the gas, and then it's also going to depend on constant, and then it's also going to depend on the temperature of the gas in Kelvin, not in degrees Celsius, but it needs to be in terms of Kelvin. Okay, so let's take a break, and then when we come back, we will show some applications of this formula.